Question 1. Examination of the data shows that a critical application requires strict control over access to sensitive customer information stored in the customer details table. The application uses several PL/SQL packages to interact with this data. Developers are considering different strategies to enforce data security and integrity. Which approach best aligns with Oracle 11g security best practices and professional standards for managing sensitive data? Option A. Implement granular privileges on the customer details table and related procedures using Oracle roles, assigning these roles to application users and service accounts. Option B. Rely solely on application-level security checks within the front-end application to restrict access to customer data. Option C. Grant the DBA role to the application service account to ensure it has all necessary permissions. Option D. Embed all data validation and access control logic directly within the PL/SQL packages that interact with the customer details table. The correct answer is A. Implement granular privileges on the customer details table and related procedures using Oracle roles, assigning these roles to application users and service accounts. Explanation. Scenario analysis. This scenario presents a common challenge in database development, ensuring data integrity and security while meeting performance requirements. Professional challenge lies in balancing the need for robust data validation and access control against the potential for performance degradation, especially in a production environment. Developers must make informed decisions about how to implement security measures that are both effective and efficient, considering the impact on end users and system administrators. The Oracle 11g environment, with its specific security features and performance characteristics, adds a layer of complexity, requiring a deep understanding of the platform's capabilities. Correct approach analysis. Implementing security at the database object level using roles and privileges is the best professional practice. This approach aligns with the principle of least privilege, ensuring that users and applications only have the necessary permissions to perform their tasks. Oracle's robust role-based access control (RBAC) mechanism allows for granular management of privileges, making it easier to audit and maintain security. By granting specific privileges on tables, views, or procedures to roles, and then assigning these roles to users, developers can effectively control data access without embedding security logic directly into application code or relying solely on application-level checks. This separation of concerns enhances security, simplifies maintenance, and improves performance by leveraging the database's native security features. This is consistent with general database security best practices and the security model inherent in Oracle 11g. Incorrect approaches analysis. Embedding all data validation and access control logic directly within PL/SQL procedures and functions, without leveraging database roles and privileges, creates several regulatory and ethical failures. Firstly, it violates the principle of separation of concerns, making the code harder to audit and maintain. If a security requirement changes, every procedure would need to be modified, increasing the risk of introducing new vulnerabilities. Secondly, it can lead to inconsistent security enforcement if not all access paths are covered by these procedures, potentially exposing sensitive data. Ethically, this approach places an undue burden on developers to be security experts for every piece of code, increasing the likelihood of oversight. Relying solely on application-level security checks without any database-level privilege enforcement is a significant security failure. This approach is vulnerable to bypass if an attacker gains direct database access or exploits a vulnerability in the application layer. It fails to meet the fundamental requirement of protecting data at its source. From a regulatory perspective, this could lead to noncompliance with data protection laws that mandate robust security measures for sensitive information. It also represents a failure in professional due diligence to implement layered security. Granting broad system-level privileges, like DBA, to application users or developers is a severe security and ethical lapse. This practice directly contradicts the principle of least privilege and opens the system to a high risk of unauthorized modifications, data breaches, or accidental data loss. It is a failure to implement basic security controls and demonstrates a lack of professional responsibility in safeguarding the data. Such an approach would likely be flagged during any security audit and could have severe legal and financial repercussions. Professional reasoning. Professionals should approach data security by first understanding the data sensitivity and the intended access patterns. The decision-making process should prioritize leveraging the database's native security features, such as roles and privileges, for robust and manageable access control. Application-level logic should focus on business rules and user interface interactions, not on fundamental security enforcement. Regular security audits and reviews of privilege assignments are crucial. When considering PL/SQL for security, it should be in conjunction with, not as a replacement for, database-level security mechanisms, and only for specific, well-defined security checks that cannot be adequately handled by roles and privileges. Question 2. Performance analysis shows that a critical PL/SQL procedure responsible for processing customer transactions is experiencing significant slowdowns, impacting the overall application responsiveness. The development team needs to assess the risks associated with various optimization strategies before implementing any changes. Which of the following approaches best represents a proactive risk assessment for addressing this performance issue in an Oracle 11g environment? Option A. Temporarily disable all security constraints and auditing features within the procedure's scope to reduce overhead, with the intention of re-enabling them after performance is improved. Option B. Analyze the execution plans of SQL statements within the procedure, identify inefficient queries, and explore alternative indexing strategies or query rewrites, while carefully considering the impact on data integrity and security. Option C. Immediately implement aggressive caching mechanisms for all data accessed by the procedure, assuming that faster data retrieval will resolve the slowdown, without detailed analysis of the procedure's logic. Option D. Manually rewrite the procedure's core logic using simpler, less robust SQL statements that are perceived to be faster, without validating their functional correctness or potential side effects. The correct answer is B. Analyze the execution plans of SQL statements within the procedure, identify inefficient queries, and explore alternative indexing strategies or query rewrites, while carefully considering the impact on data integrity and security. Explanation. This scenario is professionally challenging because it requires balancing performance optimization with the integrity and security of sensitive financial data, all within the strict confines of Oracle's 11g PL/SQL development environment and its associated best practices. The core of the challenge lies in identifying and mitigating potential risks associated with data access and manipulation, particularly when dealing with performance bottlenecks that might tempt developers to take shortcuts. The correct approach represents best professional practice because it prioritizes a systematic and secure method for identifying performance issues. By leveraging Oracle's built-in diagnostic tools and adhering to established PL/SQL coding standards, developers can pinpoint the root cause of performance degradation without compromising data security or introducing new vulnerabilities. This methodical approach ensures that any optimizations are well understood, tested, and maintainable, aligning with the principles of robust software development and data governance. The focus on understanding execution plans and identifying inefficient SQL statements is a cornerstone of Oracle performance tuning, directly addressing the risk assessment topic by proactively identifying and mitigating risks associated with poorly performing code. An incorrect approach that involves directly modifying sensitive data structures or bypassing standard security checks to test performance improvements is professionally unacceptable. This constitutes a significant regulatory and ethical failure. It violates the principle of least privilege, potentially exposing sensitive financial information to unauthorized access or modification. Furthermore, such actions can lead to data corruption, audit trail discrepancies, and noncompliance with data protection regulations, which, within the context of Oracle 11g development, would fall under the purview of data integrity and security standards expected by Oracle itself and any governing financial industry regulations. Another incorrect approach, such as relying solely on anecdotal evidence or guesswork to implement performance fixes, represents a failure in due diligence and risk assessment. It introduces a high probability of introducing new, unforeseen problems and fails to address the actual underlying cause of the performance issue, leading to wasted effort and potential system instability. Professionals should employ a structured decision-making framework when faced with performance issues. This framework should begin with a clear understanding of the problem statement and the desired outcome. Next, it involves identifying and utilizing appropriate diagnostic tools to gather objective data. This data should then be analyzed to form hypotheses about the root cause. Based on these hypotheses, potential solutions are devised, with a strong emphasis on evaluating the risks associated with each solution, particularly concerning data integrity and security. The chosen solution should then be implemented in a controlled environment, thoroughly tested and monitored post-implementation. This iterative process ensures that performance is improved responsibly and sustainably. Question 3. The performance metrics show a significant increase in the average execution time for a critical reporting procedure. The procedure is known to contain complex PL/SQL logic and interacts with multiple database tables. The development team needs to identify the most effective strategy to diagnose and resolve this performance degradation. Option A. Ignore the performance metrics, attributing the slowdown to temporary network latency or user perception. Option B. Rewrite the entire PL/SQL procedure using a different architectural approach without first identifying the specific performance bottleneck. Option C. Immediately implement a series of database parameter adjustments, assuming the issue is related to overall system resource allocation. Option D. Analyze the execution plans for SQL statements within the PL/SQL procedure, and review the PL/SQL code for inefficient constructs like row-by-row processing or poorly optimized loops. The correct answer is D. Analyze the execution plans for SQL statements within the PL/SQL procedure, and review the PL/SQL code for inefficient constructs like row-by-row processing or poorly optimized loops. Explanation. This scenario presents a professional challenge because the performance metrics, while indicating a potential issue, do not pinpoint the exact cause. Developer must exercise careful judgment to avoid making assumptions that could lead to inefficient or incorrect solutions. The core of the challenge lies in translating observed performance degradation into actionable PL/SQL code improvements, considering the constraints of the Oracle 11G environment and the specific exam's focus on advanced PL/SQL techniques. The correct approach represents best professional practice because it directly addresses the observed performance metrics by investigating the underlying PL/SQL code's efficiency. This involves a systematic review of execution plans, identifying bottlenecks such as inefficient SQL statements within PL/SQL, suboptimal loop structures, or excessive context switching. By focusing on these areas, the developer is employing a data-driven and methodical strategy aligned with best practices for performance tuning in Oracle databases. This aligns with the implicit regulatory and ethical obligation to deliver efficient and reliable software solutions, ensuring optimal resource utilization and user experience, which are critical in any professional IT environment. An incorrect approach that involves immediately rewriting complex PL/SQL logic without a clear understanding of the performance bottleneck is professionally unacceptable. This could lead to introducing new bugs, further degrading performance, or wasting valuable development time on unnecessary changes. This constitutes an ethical failure by not adhering to a disciplined development process and potentially causing harm to the application's stability and performance. Another incorrect approach, such as solely relying on database parameter tuning without examining the PL/SQL code, is also professionally unsound. While parameter tuning can impact performance, it often masks underlying code inefficiencies. This approach fails to address the root cause and can lead to a false sense of resolution, leaving the application vulnerable to future performance issues. This represents a failure to conduct a thorough risk assessment and a deviation from best practices in application performance management. A further incorrect approach might be to ignore the metrics altogether, assuming they are transient or erroneous. This is a significant professional and ethical failure. Ignoring performance indicators is a dereliction of duty, potentially leading to critical system failures, user dissatisfaction, and reputational damage. It violates the professional responsibility to maintain and improve system performance. The professional reasoning process for similar situations should involve 1. Understanding the observed symptoms, performance metrics. 2. Formulating hypotheses about potential root causes, e.g., inefficient SQL, PL/SQL logic indexing issues. 3. Gathering evidence to test hypotheses, e.g., execution plans, trace files, code reviews. 4. prioritizing and implementing solutions based on the evidence. 5. Verifying the effectiveness of the implemented solutions. 6. Documenting the process and outcomes. This structured approach ensures that solutions are targeted, effective, and minimize the risk of unintended consequences, adhering to professional standards of diligence and accountability. Question 4. Analysis of the proposed implementation of a new reporting feature that requires significant modifications to the core transaction processing tables in an Oracle 11G database. The development team is under pressure to meet a tight deadline and suggests proceeding directly with the changes, relying on their experience to anticipate and handle any issues that arise during deployment. What is the most appropriate risk management approach in this scenario? Option A. Rely on informal peer reviews of the proposed code changes and assume that the team's collective experience will prevent any significant problems. Option B. Conduct a comprehensive risk assessment to identify potential impacts on data integrity, system performance, and security, and develop mitigation and rollback plans before proceeding with the implementation. Option C. Proceed with the implementation immediately, documenting any issues encountered and addressing them reactively as they occur. Option D. Implement the changes in a production environment without prior testing, as the deadline is critical and testing would delay the release. The correct answer is B. Conduct a comprehensive risk assessment to identify potential impacts on data integrity, system performance, and security, and develop mitigation and rollback plans before proceeding with the implementation. Explanation. This scenario presents a professional challenge due to the inherent risk of data corruption or loss when implementing a critical database change without a robust risk assessment. The pressure to deliver a new feature quickly can lead to shortcuts, but in a regulated environment, adherence to established procedures and thorough risk mitigation is paramount. The professional challenge lies in balancing the urgency of business requirements with the imperative of data integrity and system stability, which are directly tied to regulatory compliance and customer trust. The correct approach represents best professional practice because it prioritizes a systematic and documented process for identifying, analyzing, and mitigating potential risks before implementing changes. This aligns with general IT governance principles and, by extension, the spirit of regulatory frameworks that mandate due diligence and risk management in data handling and system operations. Specifically, a thorough risk assessment ensures that potential impacts on data confidentiality, integrity, and availability are considered, which are core tenets of data protection regulations. It also allows for the proactive development of contingency plans, minimizing downtime and potential financial or reputational damage. An incorrect approach that bypasses a formal risk assessment for a critical database change is professionally unacceptable. This failure represents a direct disregard for due diligence and could lead to significant regulatory or ethical breaches. For instance, if the change inadvertently compromises data integrity, it could violate regulations requiring accurate record keeping or lead to misrepresentation of financial data, incurring severe penalties. Similarly, if the change causes data loss or unauthorized access, it would breach data privacy laws and erode customer trust, leading to legal repercussions and reputational damage. Another incorrect approach, such as relying solely on informal peer review without a structured risk assessment, fails to provide a documented audit trail and may overlook systemic risks that a formal process would uncover. This lack of structured evaluation can be seen as a failure to implement adequate controls, a common requirement in many regulatory frameworks. The professional decision-making process for similar situations should involve a structured approach to change management. This includes 1. Clearly defining the scope and objectives of the change. 2. Identifying all potential risks associated with the change, considering technical, operational, and security aspects. 3. Quantifying the likelihood and impact of each identified risk. 4. Developing and documenting mitigation strategies for high-priority risks. 5. Obtaining formal approval for the change based on the risk assessment and mitigation plan. 6. Implementing the change with robust monitoring and rollback capabilities. 7. Conducting a post-implementation review to assess the effectiveness of the mitigation strategies and identify lessons learned. This systematic process ensures that decisions are informed, documented, and aligned with regulatory expectations and best practices for system stability and data integrity. Question 5. Governance review demonstrates that a critical PL/SQL procedure responsible for processing customer order data has been flagged for potential data integrity issues. The current risk assessment process for this procedure primarily relies on basic syntax checks and a limited set of positive test cases. What is the most appropriate approach to enhance the risk assessment for this PL/SQL procedure to ensure data accuracy and prevent future issues? Option A. Conduct a performance tuning exercise on the PL/SQL procedure to ensure it executes as quickly as possible, as performance issues can sometimes lead to data inconsistencies. Option B. Implement a comprehensive testing strategy that includes negative test cases, boundary value analysis, and integration testing with related database objects, alongside a thorough review of the procedure's business logic and error handling mechanisms. Option C. Expand the existing positive test cases to cover a wider range of typical customer order scenarios, without altering the fundamental approach to risk assessment. Option D. Rely on automated static code analysis tools to identify any potential vulnerabilities or deviations from coding standards, assuming these tools will catch all data integrity risks. The correct answer is B. Implement a comprehensive testing strategy that includes negative test cases, boundary value analysis, and integration testing with related database objects, alongside a thorough review of the procedure's business logic and error handling mechanisms. Explanation: scenario analysis. This scenario presents a common challenge in software development and database management, where a critical business process relies on a PL/SQL procedure. The challenge lies in ensuring the integrity and accuracy of the data processed by this procedure, especially when dealing with potentially large and varied datasets. The governance review highlights a potential weakness in the existing risk assessment process, implying that the current methods might not be sufficiently robust to identify and mitigate all relevant risks. The need for a more comprehensive approach to risk assessment for PL/SQL code is paramount to prevent data corruption, financial misstatements, or operational disruptions. Correct approach analysis. The correct approach involves a multifaceted risk assessment that goes beyond simple code review. It necessitates a thorough understanding of the business logic embedded within the PL/SQL procedure, its interaction with other database objects, and the potential impact of errors. This includes analyzing the data types, constraints, and potential for data anomalies that the procedure might encounter. Furthermore, it requires considering various error conditions, such as invalid input data, constraint violations, and unexpected system states, and how the procedure handles them. The use of comprehensive test cases, including boundary conditions and negative testing, is crucial to validate the procedure's behavior under diverse scenarios. This approach aligns with best practices in software quality assurance and data governance, aiming to proactively identify and address risks before they manifest in production, thereby ensuring data integrity and system reliability. Incorrect approaches analysis. One incorrect approach is to solely rely on static code analysis tools without understanding the business context. While these tools can identify syntax errors or potential performance issues, they often fail to grasp the nuances of business logic or the impact of specific data values. This can lead to overlooking critical risks related to data integrity or incorrect business rule enforcement, a failure in professional due diligence. Another incorrect approach is to assume that unit testing alone is sufficient. Unit tests, while valuable, typically focus on isolated components. If the PL/SQL procedure interacts with other database objects or relies on specific data states, unit tests might not adequately cover integration risks or end-to-end data flow issues. This oversight can result in a false sense of security, neglecting risks that only emerge when the procedure operates within its full environment. Failure to conduct a holistic risk assessment. A third incorrect approach is to prioritize performance optimization over functional correctness and data integrity. While performance is important, it should not come at the expense of ensuring the procedure accurately processes data according to business requirements. Focusing solely on making the procedure faster without verifying its accuracy can lead to subtle data corruption or incorrect business outcomes. A significant ethical and professional failing in data management. Professional reasoning. Professionals should adopt a risk-based approach to PL/SQL development and maintenance. This involves understanding the criticality of the procedure to business operations, the sensitivity of the data it handles, and the potential impact of failure. A structured risk assessment process should include identifying potential risks, e.g., data corruption, incorrect calculations, security vulnerabilities, analyzing the likelihood and impact of each risk, and defining mitigation strategies, e.g., enhanced testing, code reviews, input validation, error handling. Regular review and updates to the risk assessment are also essential, especially when the procedure or its underlying data structures are modified. This systematic approach ensures that resources are focused on the most significant risks, leading to more robust and reliable PL/SQL solutions. Question 6. System analysis indicates that a critical PL/SQL package for generating end-of-quarter financial reports is experiencing significant performance degradation, impacting the timely submission of regulatory filings. The development team has identified a potential optimization within the package, but implementing it requires extensive code refactoring and thorough testing. Management is pressuring for an immediate fix to avoid penalties, which approach best balances the need for speed with the imperative of maintaining data integrity and application stability. Option A. Immediately deploy the optimized code to the production environment to resolve the reporting delay and address any unforeseen issues that arise through post-deployment hotfixes. Option B. Conduct a focused risk assessment specifically on the proposed code refactoring, prioritizing potential impacts on data integrity and reporting accuracy, and implement the optimization only after defining and verifying mitigation strategies for identified risks. Option C. Implement the optimization using the identified code refactoring, relying on informal testing by senior developers to ensure correctness, and defer a formal risk assessment until after the next reporting cycle. Option D. Revert the package to a previous, stable version that does not have the performance issue, even if it means delaying the introduction of new reporting features, and schedule a comprehensive risk assessment for the optimization at a later, less critical time. The correct answer is B. Conduct a focused risk assessment specifically on the proposed code refactoring, prioritizing potential impacts on data integrity and reporting accuracy, and implement the optimization only after defining and verifying mitigation strategies for identified risks. Explanation. This scenario presents a professional challenge due to the inherent conflict between the need for rapid deployment of critical financial reporting functionality and the imperative to maintain data integrity and security. The pressure to deliver quickly can lead to shortcuts that bypass established risk assessment protocols, potentially exposing the organization to significant financial and reputational damage. Careful judgment is required to balance these competing demands. The correct approach represents best professional practice because it systematically identifies, analyzes, and mitigates potential risks before implementation. This aligns with the principles of robust IT governance and secure software development lifecycle management, which are implicitly expected within the Oracle 11g development context. By prioritizing a thorough risk assessment, the development team ensures that potential vulnerabilities are addressed proactively, thereby safeguarding data integrity, application performance, and compliance with any relevant, though not explicitly stated in this exam context, generally understood financial regulations. This methodical approach minimizes the likelihood of costly post-deployment fixes and reputational harm. An incorrect approach that bypasses formal risk assessment for speed fails to uphold professional responsibility. It represents a regulatory and ethical failure by disregarding established best practices for secure and reliable software development. This can lead to data breaches, incorrect financial reporting, and potential noncompliance with industry standards, all of which carry severe consequences. Another incorrect approach that relies solely on informal peer review, while valuable, is insufficient as it lacks the structured methodology and comprehensive scope of a formal risk assessment. It may miss systemic risks or fail to document mitigation strategies adequately, leaving the organization exposed. A third incorrect approach that defers risk assessment to the post-implementation phase is fundamentally flawed. It signifies a reactive rather than proactive stance, increasing the likelihood of significant issues arising during or immediately after deployment, which are far more difficult and expensive to rectify. Professionals should employ a decision-making framework that prioritizes risk management throughout the development lifecycle. This involves understanding the business criticality of the feature, identifying potential threats and vulnerabilities, assessing the likelihood and impact of these risks, and developing appropriate mitigation strategies. When faced with time constraints, the focus should be on streamlining the risk assessment process without compromising its effectiveness, perhaps by prioritizing high-impact risks or leveraging automated tools, rather than eliminating it entirely. Question 7. Research into best practices for developing advanced PL/SQL code in Oracle 11g. A senior developer is tasked with creating a complex data processing package. The team's existing codebase exhibits varying levels of quality, and there's a push to improve overall maintainability and reduce future debugging efforts. The developer needs to decide on the most appropriate strategy for structuring and writing the PL/SQL code within this package to exemplify professional excellence. Which of the following approaches best aligns with these objectives? Option A. Utilize global package variables extensively to pass data between different sections of the package, simplifying data access and reducing the need for explicit parameter passing. Option B. Focus on writing the most concise code possible, minimizing variable declarations and comments to reduce the overall code footprint, assuming developers can infer logic from context. Option C. Prioritize writing clear, modular, and well-commented PL/SQL code, breaking down complex logic into smaller, reusable procedures and functions, and employing consistent naming conventions and indentation. Option D. Implement aggressive performance optimizations by using complex, nested SQL queries directly within the PL/SQL logic, and avoiding the creation of separate procedures or functions for distinct tasks. The correct answer is C. Prioritize writing clear, modular, and well-commented PL/SQL code, breaking down complex logic into smaller, reusable procedures and functions, and employing consistent naming conventions and indentation. Explanation. This scenario presents a professional challenge in managing PL/SQL code quality and maintainability within a project adhering to Oracle 11g standards. The core difficulty lies in balancing the immediate need for functional code with the long-term implications of technical debt and adherence to established best practices for advanced PL/SQL development. Careful judgment is required to select an approach that not only delivers the required functionality, but also ensures the code is robust, efficient, and easily maintainable by other developers, aligning with the principles of good software engineering. The correct approach represents best professional practice because it prioritizes code clarity, modularity, and adherence to established Oracle PL/SQL coding standards. This includes using meaningful variable names, consistent indentation, appropriate commenting, and breaking down complex logic into smaller, reusable procedures or functions. Such practices directly contribute to reduced debugging time, easier code reviews, and a lower risk of introducing errors during future modifications. From a regulatory and ethical standpoint, this approach demonstrates a commitment to producing high-quality, auditable code, which is implicitly expected in professional software development environments, even without explicit external regulations for this specific exam context. It fosters a culture of accountability and professionalism. An incorrect approach that involves writing dense, uncommented code with minimal error handling is professionally unacceptable. This failure stems from a disregard for maintainability and readability, leading to increased technical debt. Ethically, it can be seen as a failure to uphold professional standards by creating code that is difficult for others to understand or work with, potentially causing delays or errors for the team. Another incorrect approach, focusing solely on performance optimization without considering code structure, might lead to obfuscated and brittle code. While performance is important, sacrificing clarity and maintainability for marginal gains can be a false economy, leading to higher long-term costs in maintenance and debugging. This also represents a failure to apply a balanced, professional approach to software development. A third incorrect approach, relying heavily on global variables for data sharing, introduces hidden dependencies and makes the code harder to reason about and test. This is a known anti-pattern that increases the likelihood of unintended side effects and makes refactoring significantly more challenging, demonstrating a lack of foresight and adherence to sound programming principles. The professional decision-making process for similar situations should involve a systematic evaluation of potential solutions against key criteria: functionality, performance, maintainability, readability, and adherence to established coding standards. Developers should consider the long-term impact of their choices, not just the immediate outcome. This involves asking, will this code be easy for another developer to understand and modify in 6 months? And does this approach align with the project's established coding guidelines and best practices? Prioritizing clear, modular, and well-documented code, even if it requires slightly more upfront effort, is a hallmark of professional software development. Question 8. The performance metrics show a significant increase in query execution times for a critical reporting application. Upon initial investigation, several PL/SQL procedures responsible for data aggregation and presentation are identified as potential culprits. The development team is considering several strategies to address this performance degradation. Which of the following strategies represents the most professional and effective approach to resolving this issue? Option A. Rewrite the entire PL/SQL code base using a different programming paradigm, such as a functional approach, without first identifying the specific performance bottlenecks within the existing code. Option B. Immediately add all rows hints to all SQL statements within the problematic PL/SQL procedures to encourage the optimizer to prioritize full table scans, as this often speeds up initial data retrieval. Option C. Systematically analyze the execution plans of the SQL statements within the identified PL/SQL procedures, identify inefficient SQL constructs or missing indexes, and refactor the SQL or add appropriate indexes based on the analysis. Option D. Focus on increasing the memory allocated to the Oracle database instance and upgrading the server hardware, assuming that the current infrastructure is insufficient to handle the reporting workload. The correct answer is C. Systematically analyze the execution plans of the SQL statements within the identified PL/SQL procedures, identify inefficient SQL constructs or missing indexes, and refactor the SQL or add appropriate indexes based on the analysis. Explanation. The performance metrics show a significant increase in query execution times for a critical reporting application. This scenario is professionally challenging because it directly impacts business operations and user productivity. The development team must identify the root cause of the performance degradation and implement a solution that not only resolves the issue, but also adheres to best practices for maintainability and future scalability. The pressure to deliver a quick fix must be balanced against the need for a robust and well-reasoned solution. The correct approach involves a systematic and data-driven investigation into the PL/SQL code responsible for the reporting. This includes analyzing execution plans, identifying inefficient SQL statements within the PL/SQL blocks, and considering the impact of data volume and distribution. Best professional practice dictates that performance tuning should be based on objective measurements and a thorough understanding of the Oracle optimizer's behavior. This approach ensures that the implemented solution is effective, sustainable, and minimizes the risk of introducing new performance bottlenecks or functional regressions. Adherence to Oracle's recommended tuning methodologies, as outlined in their documentation and best practice guides, is paramount. An incorrect approach would be to make arbitrary changes to the PL/SQL code without proper analysis. For instance, simply adding hints to SQL statements without understanding their impact or the underlying data structure can lead to suboptimal performance or even worse execution plans. This is a failure of professional due diligence and can be considered a breach of professional responsibility to deliver quality software. Another incorrect approach is to focus solely on hardware upgrades without investigating the software's efficiency. While hardware can play a role, inefficient code will continue to strain resources, regardless of their capacity. This demonstrates a lack of understanding of the application's architecture and a tendency to address symptoms rather than causes, which is unprofessional and wasteful. Professionals should approach such situations by first establishing a baseline of current performance. Then, they should use Oracle's diagnostic tools, e.g., Explain Plan, SQL Trace, TK-Prof, DBMS Profiler, to pinpoint the specific PL/SQL units and SQL statements contributing to the performance degradation. The next step is to analyze the execution plans and identify areas for optimization, such as missing indexes, inefficient join methods, or unnecessary data retrieval. Solutions should be tested in a development or staging environment that mirrors production as closely as possible before deployment. This systematic evidence-based approach ensures that decisions are informed and that the implemented solution is the most effective and efficient. Question 9. Operational review demonstrates that a critical PL/SQL package, responsible for processing financial transactions, requires significant refactoring to improve performance and incorporate new business logic. The development team has proposed several approaches to implement these changes. Which approach best balances the need for modernization with the imperative to maintain system stability and data integrity? Option A. Conduct thorough static code analysis to identify dependencies. Develop comprehensive unit and integration test suites covering all identified risks, and implement a well-defined rollback strategy before deploying to a staging environment for final validation. Option B. Focus solely on optimizing the performance aspects of the package, deferring the incorporation of new business logic until a subsequent release to minimize the scope of the current change. Option C. Implement the refactoring directly in the production environment, relying on immediate post-deployment monitoring and manual rollback if critical errors are detected. Option D. Proceed with the refactoring based on the lead developer's extensive experience with the package, performing only basic functional tests on a development instance before deploying to production. The correct answer is C. Implement the refactoring directly in the production environment, relying on immediate post-deployment monitoring and manual rollback if critical errors are detected. Explanation. Scenario analysis. The scenario presents a common challenge in advanced PL/SQL development, managing the impact of significant code changes on existing, critical functionalities. The core difficulty lies in balancing the need for innovation and improvement with the imperative to maintain system stability and data integrity. Developers must anticipate unintended consequences, especially when dealing with complex logic, large datasets, or integrations with other systems. The pressure to deliver new features quickly can sometimes overshadow the meticulous planning required for robust impact assessment, leading to potential production issues. Correct approach analysis. The correct approach involves a systematic and thorough impact assessment process that leverages PL/SQL's advanced features for analysis and testing. This includes using static analysis tools to identify dependencies and potential conflicts, creating comprehensive unit tests that cover edge cases and boundary conditions, and performing integration testing to validate interactions with other modules. Furthermore, employing techniques like code reviews, version control with detailed commit messages, and rollback strategies ensures that any unforeseen issues can be quickly identified and mitigated. This methodical approach aligns with best practices for software development lifecycle management, emphasizing proactive risk mitigation and ensuring that changes are well understood and validated before deployment. It directly supports the principle of maintaining system integrity and minimizing disruption, which are paramount in regulated environments where system availability and data accuracy are critical. Incorrect approaches analysis. One incorrect approach is to proceed with the changes based solely on developer intuition or limited testing of the immediate code block. This fails to account for the ripple effects of modifications within a complex PL/SQL application. It represents a significant regulatory and ethical failure by disregarding the responsibility to ensure system stability and data integrity. Such an approach increases the likelihood of introducing bugs, data corruption, or performance degradation, which can have severe consequences, including financial loss, reputational damage, and non-compliance with service-level agreements or industry regulations. Another incorrect approach is to rely exclusively on manual testing performed by end users after deployment. While user feedback is valuable, it is not a substitute for rigorous pre-deployment testing. This method is reactive rather than proactive and places an undue burden on users to identify technical issues. Ethically and regulatorily, this is unacceptable as it outsources the responsibility for quality assurance to the end users and exposes the organization to significant risk of operational failure. It demonstrates a lack of due diligence in the development process. A third incorrect approach is to implement the changes in a production environment without a proper rollback plan. This is a highly risky strategy that can lead to catastrophic system failures if issues arise. It violates fundamental principles of change management and operational risk management. From a regulatory perspective, it can be seen as gross negligence, potentially leading to breaches of compliance requirements related to system availability and data security. Professional reasoning. Professionals should approach significant PL/SQL code changes by first establishing a clear understanding of the existing system's architecture and dependencies. This involves engaging with senior developers, architects, and business stakeholders to gather requirements and identify potential risks. The next step is to design and execute a comprehensive impact assessment plan, which includes static code analysis, unit testing, integration testing, and performance testing. Version control should be used meticulously, with clear documentation of changes. A robust rollback strategy must be in place before any deployment. Finally, a phased rollout or canary deployment can be considered for high-risk changes to further mitigate potential issues. This structured decision-making process prioritizes risk management, quality assurance, and adherence to professional standards. Question 10. Which approach would be most appropriate for ensuring that error logging within a PL/SQL procedure persists even if the main transaction that invoked the procedure is subsequently rolled back? Option A. Use a global variable to store error messages and log them after the main transaction completes. Option B. Commit the main transaction before executing the error logging statements. Option C. Declare the logging procedure as an autonomous transaction using the autonomous transaction pragma. Option D. Include the error logging statements directly within the main transaction's code block. The correct answer is C. Declare the logging procedure as an autonomous transaction using the autonomous transaction pragma. Explanation. Scenario analysis. This scenario presents a common challenge in advanced PL/SQL development, managing the lifecycle and potential impact of autonomous transactions within a larger, transactional context. Developers must balance the need for independent operations, like logging or auditing, with the integrity of the main transaction. Mismanagement can lead to data inconsistencies, rollback failures, and violations of transactional integrity principles, which are critical for maintaining data accuracy and reliability in any Oracle database environment. The challenge lies in understanding the subtle interactions and isolation levels of autonomous transactions. Correct approach analysis. The correct approach involves carefully designing the autonomous transaction to perform its specific, isolated task and ensuring it commits or rolls back independently of the main transaction. This is best professional practice because it adheres to the principle of transactional isolation. Autonomous transactions are designed precisely for scenarios where a subtransaction needs to execute independently, such as logging errors, updating audit trails, or performing operations that should not be affected by the rollback of the main transaction. By explicitly defining the scope and commit/rollback behavior of the autonomous transaction, developers ensure that the main transaction's integrity is preserved while still achieving the desired independent operation. This aligns with Oracle's best practices for managing complex transactional logic and maintaining data consistency. Incorrect approaches analysis. An approach that attempts to directly include operations that should be autonomous within the main transaction, without using the autonomous transaction pragma, would fail because it would subject these operations to the same commit or rollback as the main transaction. If the main transaction rolls back, these operations would be lost, defeating their purpose, e.g., logging an error that occurred during the main transaction. This represents a failure to understand and apply the fundamental isolation mechanisms provided by Oracle. Another incorrect approach might involve committing within the main transaction before completing all logically related operations. This breaks transactional atomicity, where all parts of a logical unit of work should succeed or fail together. If an autonomous transaction is intended to record a success or failure that is contingent on the main transaction's outcome, committing the main transaction prematurely would lead to an inconsistent state. A third incorrect approach could be to simply ignore the need for isolation and let all operations run within the main transaction, even if some are intended for independent logging or auditing. This would mean that audit logs or error records would be rolled back if the main transaction fails, rendering them useless for post-mortem analysis or debugging. This is a failure to leverage the specific features designed for such scenarios, leading to a less robust and maintainable application. Professional reasoning. Professionals should approach such scenarios by first clearly defining the transactional boundaries and dependencies of each operation. When an operation needs to execute independently of the main transaction's commit or rollback behavior, the autonomous transaction pragma is the appropriate mechanism. Developers should ask, Does this operation need to persist its changes even if the calling transaction fails? If the answer is yes, an autonomous transaction is likely required. This systematic evaluation ensures that transactional integrity is maintained while leveraging Oracle's features for robust application design. Question 11. The review process indicates that a critical stored procedure, responsible for generating daily sales reports, is experiencing significant performance degradation, leading to delayed report generation. The development team is considering several strategies to address this issue. Which of the following strategies represents the most professional and effective approach to resolving the performance bottleneck? Option A. Randomly rewrite SQL queries within the procedure, hoping to stumble upon a more efficient version without prior analysis. Option B. Proactively analyze the execution plans of the SQL statements within the stored procedure using Oracle's diagnostic tools and optimize based on the findings. Option C. Immediately upgrade the server hardware to provide more processing power and memory, assuming the issue is resource-related. Option D. Ignore the performance warnings generated by the Oracle Optimizer, as the procedure is still producing the correct output. The correct answer is B. Proactively analyze the execution plans of the SQL statements within the stored procedure using Oracle's diagnostic tools and optimize based on the findings. Explanation. The review process indicates a common challenge in advanced PL/SQL development, managing the performance implications of complex data retrieval within stored procedures, particularly when dealing with large datasets. The professional challenge lies in balancing the need for comprehensive data analysis with the imperative to maintain system responsiveness and resource efficiency. Developers must make informed decisions about data access strategies that are not only functionally correct, but also adhere to best practices for performance optimization, which indirectly impacts system availability and operational costs, aligning with general principles of responsible IT resource management. The correct approach represents best professional practice because it prioritizes a proactive and analytical method to identify and address performance bottlenecks. By utilizing Oracle's built-in performance tuning tools, such as Explain Plan and SQL Trace, developers can gain granular insights into query execution. This allows for targeted optimization of SQL statements, indexing strategies, and PL/SQL code logic. This methodical approach ensures that performance issues are resolved at their root cause, leading to sustainable improvements and preventing future degradation. It aligns with the professional responsibility to deliver efficient and reliable software solutions. An incorrect approach that relies solely on increasing hardware resources without investigating the underlying code is professionally unacceptable. This represents a failure to apply due diligence in performance tuning. It can lead to escalating operational costs and masks underlying inefficiencies that will likely resurface or manifest in other areas. Ethically, it can be seen as a wasteful allocation of resources. Another incorrect approach, which involves arbitrarily rewriting SQL statements without a clear understanding of their execution plan or the impact on data retrieval, is also professionally unsound. This can introduce new performance problems or even alter the data returned, leading to functional errors. It demonstrates a lack of systematic problem solving and a disregard for the potential consequences of code changes. A further incorrect approach, such as ignoring performance warnings from the Oracle Optimizer because the code works, is a significant professional failing. The optimizer's warnings are indicators of potential inefficiencies. Disregarding them suggests a lack of commitment to optimal code design and can lead to suboptimal performance that impacts users and system stability over time. The professional decision-making process for similar situations should involve a structured approach. 1. Identify the symptom, performance degradation. 2. Gather data. Utilize Oracle's diagnostic tools, Explain Plan, SQL Trace, AWR reports to understand the execution path and resource consumption of the problematic PL/SQL code. 3. Analyze the data. Pinpoint the specific SQL statements or PL/SQL constructs that are causing the performance issues. 4. Formulate hypotheses. Based on the analysis, propose potential solutions, e.g., indexing, query rewriting, algorithm changes. 5. Test and validate. Implement proposed solutions in a controlled environment and measure their impact on performance. 6. Deploy and monitor. Once validated, deploy the optimized code and continue to monitor performance to ensure sustained improvement. Question 12. The analysis reveals that a critical reporting function within an Oracle 11G application is experiencing significant performance degradation when processing large volumes of historical sales data. The current implementation involves a complex PL/SQL procedure that executes a series of multi-table joins and aggregations to generate summary reports. Developers are considering alternative strategies to improve the execution time of this procedure, which is impacting the availability of real-time sales insights. Which of the following approaches best addresses the performance challenge while adhering to professional best practices for database development and system reliability? Option A. Refactor the PL/SQL procedure to perform the complex multi-table joins and aggregations directly within the procedure's SQL statements, without altering the data retrieval strategy. Option B. Enhance the existing indexes on the base tables involved in the joins and aggregations, assuming this will sufficiently optimize the query. Option C. Rewrite the PL/SQL procedure to fetch all raw transaction data into PL/SQL collections and perform all aggregations within the procedural logic. Option D. Implement materialized views that pre-aggregate and store the required summary data, configured for an appropriate refresh strategy to maintain data currency. The correct answer is D. Implement materialized views that pre-aggregate and store the required summary data, configured for an appropriate refresh strategy to maintain data currency. Explanation. The scenario presents a common challenge in advanced PL/SQL development, optimizing performance for large datasets within a transactional system. The professional challenge lies in balancing the need for efficient data retrieval and manipulation with the imperative to maintain data integrity and adhere to strict performance SLAs. Developers must consider not only the immediate impact of their code, but also its long-term maintainability and scalability. The correct approach, leveraging materialized views with appropriate refresh strategies, represents best professional practice because it directly addresses the performance bottleneck by pre-computing and storing complex query results. This significantly reduces the execution time for frequently accessed, aggregated, or joined data. Oracle's materialized view technology is designed for such scenarios, offering robust mechanisms for maintaining data freshness without requiring full query re-execution. The choice of a fast refresh strategy, where applicable, further minimizes the overhead associated with keeping the materialized view synchronized with the base tables, aligning with the principle of efficient resource utilization. This approach is supported by Oracle's best practices for performance tuning and data warehousing. An incorrect approach involving the creation of a complex, multi-table join within a stored procedure that is executed frequently for reporting purposes fails to meet best professional practice. This is because such an approach leads to repeated, resource-intensive computations, directly impacting application responsiveness and potentially causing contention on base tables. From a regulatory or ethical standpoint, this represents a failure to deliver a performant and reliable system, which can have downstream consequences on business operations and user trust. It also demonstrates a lack of due diligence in performance optimization, which is an implicit expectation in professional software development. Another incorrect approach, relying solely on indexing without considering the complexity of the query, is also professionally deficient. While indexes are crucial for query performance, they are not a panacea. For queries involving complex joins and aggregations across many tables, indexes alone may not provide sufficient performance gains, and in some cases can even degrade performance due to the overhead of maintaining them and the optimizer's inability to effectively use them for the specific query pattern. This approach neglects a deeper analysis of query execution plans and data access patterns, leading to suboptimal solutions. Ethically, it can be seen as a failure to adequately address performance requirements, potentially leading to system instability or unreliability. A third incorrect approach, involving the retrieval of all raw data into the PL/SQL code and performing aggregations within the procedural logic, is highly inefficient and professionally unsound. This method bypasses the database's optimized query execution engine, leading to excessive data transfer, increased memory usage within the PL/SQL environment, and significantly slower processing times. It also makes the code harder to maintain and debug. This approach represents a fundamental misunderstanding of how to leverage the database for data processing and can be considered a failure to adhere to established database development best practices, potentially impacting system stability and data integrity due to the increased complexity and potential for errors in manual aggregation. The professional decision-making process for similar situations should involve a systematic approach. 1. Performance profiling. Identify the specific queries or operations that are causing performance bottlenecks. 2. Query analysis. Utilize tools like Explain Plan and SQL Trace to understand the execution plan of problematic queries. 3. Solution design. Evaluate various optimization techniques, including indexing, query rewriting, materialized views, and appropriate PL/SQL constructs. 4. Impact assessment. Consider the trade-offs of each potential solution in terms of performance, maintainability, complexity, and resource utilization. 5. Implementation and testing. Implement the chosen solution and rigorously test its performance and impact on the overall system. 6. Monitoring and iteration. Continuously monitor performance and be prepared to iterate on the solution as data volumes or usage patterns change. Question 13. The monitoring system demonstrates a recurring pattern of generic Aura 06502, PL/SQL, numeric or value error messages originating from a critical data processing package. This package utilizes advanced PL/SQL features for data validation and transformation. The development team is considering several strategies to address these frequent, unspecific errors. Which of the following approaches best addresses the underlying issue and adheres to professional best practices for managing PL/SQL exceptions in Oracle 11g? Option A. Implement custom exceptions within the package to specifically identify the nature of the numeric or value errors, and use raise application error to return meaningful error codes and messages to the calling environment. Option B. Update the package to catch all exceptions generically and log them to a separate table without re-raising them, ensuring the calling program continues execution uninterrupted. Option C. Refactor the package to remove all explicit exception handling blocks, relying solely on Oracle's default error propagation mechanisms to surface issues. Option D. Modify the package to simply ignore all ORA 06502 errors, assuming they are transient and will resolve themselves, thereby reducing the noise in the monitoring system. The correct answer is A. Implement custom exceptions within the package to specifically identify the nature of the numeric or value errors, and use raise application error to return meaningful error codes and messages to the calling environment. Explanation. This scenario presents a professional challenge in ensuring the integrity and performance of PL/SQL code within a critical Oracle 11g environment. The challenge lies in balancing the need for efficient code execution with the potential for unintended side effects or performance degradation introduced by advanced PL/SQL features, particularly those related to exception handling and error propagation. Adhering to best practices is paramount to maintain system stability and prevent data corruption or service interruptions, which could have significant financial and reputational consequences. The correct approach represents best professional practice because it prioritizes robust error handling and clear propagation mechanisms by explicitly defining custom exceptions and using the raise application error procedure. Developers create predictable and manageable error conditions. This allows downstream applications and monitoring tools to accurately identify, log, and respond to specific issues, facilitating quicker resolution and preventing cascading failures. This aligns with the general principles of software engineering best practices, emphasizing clarity, maintainability, and fault tolerance, which are implicitly expected in professional Oracle development. An incorrect approach that relies on implicit exception propagation without explicit handling or custom error messages is professionally unacceptable. This failure to clearly define and communicate errors can lead to ambiguous error codes or generic messages that obscure the root cause of a problem. This makes debugging significantly more difficult and time-consuming, increasing the risk of prolonged downtime or incorrect data manipulation. From a regulatory or ethical standpoint, this lack of clarity can be seen as a failure to exercise due diligence in developing reliable software, potentially violating implicit professional standards for quality and accountability. Another incorrect approach that involves suppressing exceptions without proper logging or re-raising them is also professionally flawed. This practice creates silent failures, where errors occur but are not visible to developers or administrators. This can lead to data inconsistencies or unexpected application behavior that goes unnoticed until it causes a major incident. Ethically, this is a failure to be transparent about the system's operational status and can lead to a loss of trust if issues are discovered after the fact. It demonstrates a lack of responsibility in ensuring the system's integrity. The professional decision-making process for similar situations should involve a thorough understanding of the potential impact of PL/SQL code on the overall system. Developers must consider not only the functional correctness, but also the robustness of error handling. This involves anticipating potential failure points, defining clear exception handling strategies, and implementing mechanisms for effective error reporting and logging. A systematic approach, including code reviews and thorough testing of exception scenarios, is crucial to ensure that the code is not only functional, but also resilient and maintainable. Question 14. The risk matrix shows a high likelihood of data corruption due to concurrent DML operations on a critical table used for trade settlement. The business requires near real-time processing, but data integrity is paramount for regulatory reporting. Which PL/SQL implementation strategy best mitigates this risk while adhering to Oracle 11g's concurrency control mechanisms? Option A. Implement explicit row-level locking within PL/SQL procedures using select for update, combined with appropriate transaction isolation levels, to ensure that concurrent transactions acquire locks on the specific rows they are modifying, preventing race conditions and data corruption. Option B. Implement autonomous transactions for each DML operation on the critical table to isolate them from the main transaction, allowing them to commit or roll back independently without affecting the parent transaction's locks. Option C. Disable Oracle's automatic locking mechanisms for this table and implement custom application-level validation, logic to detect and prevent concurrent modifications, relying on the application to manage data consistency. Option D. Utilize table-level locks within PL/SQL procedures to serialize all access to the critical table, ensuring only one transaction can modify data at any given time, thereby preventing corruption. Correct answer is A. Implement explicit row-level locking within PL/SQL procedures using select for update, combined with appropriate transaction isolation levels, to ensure that concurrent transactions acquire locks on the specific rows they are modifying, preventing race conditions and data corruption. Explanation. The risk matrix shows a high likelihood of data corruption due to concurrent DML operations on a critical table. This scenario is professionally challenging because it directly impacts data integrity, a fundamental requirement for any financial system. The pressure to maintain high availability for trading operations conflicts with the need for robust data protection. Choosing the wrong approach can lead to significant financial losses, regulatory penalties, and reputational damage. The correct approach involves implementing a robust locking strategy that balances concurrency and data integrity. Using row-level locking with appropriate transaction isolation levels, such as read committed or serializable, ensures that concurrent transactions do not interfere with each other's data, preventing corruption. This aligns with best practices for data management and regulatory compliance, as it upholds the principle of data accuracy and reliability. Oracle's advanced PL/SQL features, like autonomous transactions or carefully managed explicit locking, can be leveraged to achieve this without excessive downtime. An incorrect approach would be to disable or bypass Oracle's built-in locking mechanisms to improve performance. This is a severe regulatory and ethical failure because it directly compromises data integrity, violating principles of accurate financial reporting and auditability. Another incorrect approach is to rely solely on application-level checks without proper database-level locking. While application logic can detect some anomalies, it cannot prevent race conditions at the database level, leading to data corruption that is difficult to detect and rectify, thus failing to meet the standard of care expected in financial data handling. A third incorrect approach is to implement a coarse-grained locking mechanism, such as table locks, which would severely degrade performance and availability, failing to meet the business requirement for high concurrency, even though it might prevent corruption. Professionals should approach this by first understanding the specific business impact of data corruption versus performance degradation. They should then evaluate Oracle's concurrency control mechanisms, considering the trade-offs between isolation levels and performance. The decision-making process should involve consulting with database administrators and business stakeholders to agree on an acceptable risk tolerance, and then implementing the most appropriate locking strategy using advanced PL/SQL techniques to minimize impact while ensuring data integrity. Question 15. During the evaluation of a critical financial reporting application's PL/SQL code, a developer proposes using an autonomous transaction to log all exceptions encountered during the generation of monthly reports. The primary reporting logic involves complex calculations and updates to summary tables, all within a single, large transaction. The developer argues that logging errors independently ensures that the error log is always updated, even if the main reporting transaction fails and rolls back. What is the most appropriate approach to handle exception logging in this scenario, considering the need for data integrity and a reliable audit trail? Option A. Log exceptions directly within the main transaction's exception handler, allowing them to be rolled back if the main transaction fails, and rely on application-level retry mechanisms for critical errors. Option B. Implement a separate, dedicated logging table that is updated using standard insert statements within the main transaction's exception handler, and design the application to handle potential rollback of these log entries. Option C. Implement the exception logging within a clearly defined autonomous transaction, ensuring it commits independently of the main reporting transaction. Option D. Use an autonomous transaction to log exceptions, but ensure that the autonomous transaction's commit is conditional on the success of the main reporting transaction. The correct answer is C. Implement the exception logging within a clearly defined autonomous transaction, ensuring it commits independently of the main reporting transaction. Explanation. Scenario analysis. This scenario presents a professional challenge related to managing database security and data integrity within the context of PL/SQL development, specifically concerning the use of autonomous transactions. The core difficulty lies in balancing the need for robust error handling and transactional isolation with the potential for unintended side effects and security vulnerabilities that autonomous transactions can introduce if not implemented with extreme care. Developers must make informed decisions about when and how to employ this powerful but potentially risky feature, ensuring that its use aligns with application requirements and security policies. The challenge is amplified by the need to prevent unauthorized data modifications or bypasses of critical business logic, which could have significant operational and compliance implications. Correct approach analysis. The correct approach involves carefully designing the PL/SQL code to leverage autonomous transactions only when strictly necessary for specific, isolated operations that must commit or roll back independently of the main transaction. This typically includes logging errors, auditing critical events, or performing independent data validation checks that should not affect the outcome of the primary business transaction. The key is to encapsulate these operations within a separate, clearly defined autonomous transaction block, ensuring that the main transaction's integrity is preserved. This approach adheres to best practices by minimizing the scope of autonomous transactions, thereby reducing the risk of data corruption or unexpected behavior. It also aligns with the principle of least privilege and robust error handling, ensuring that critical application logic remains unaffected by the independent commit or rollback of auxiliary operations. Incorrect approaches analysis. Using an autonomous transaction for general-purpose error logging without considering the implications on the main transaction state is a regulatory and ethical failure. It can lead to situations where errors are logged, but the main transaction, which might have failed due to the same underlying issue, is rolled back. This creates an inconsistent audit trail and can mask critical failures, violating data integrity and auditability requirements. Implementing an autonomous transaction to bypass a constraint or business rule in the main transaction is a severe ethical and regulatory violation. It undermines the integrity of the application's business logic and data validation mechanisms, potentially leading to the storage of invalid or inconsistent data. This directly contravenes principles of data accuracy and compliance with business policies. Employing an autonomous transaction to perform operations that are intrinsically linked to the main transaction's success or failure, such as updating core application data, is fundamentally flawed. If the main transaction rolls back, the data updated by the autonomous transaction might remain, leading to data inconsistencies and a corrupted application state. This violates the principle of transactional atomicity and can lead to significant data integrity issues, posing a risk to operational stability and potentially violating data governance policies. Professional reasoning. Professionals should approach the use of autonomous transactions with a strong understanding of their transactional behavior and potential impact. The decision-making process should involve 1. Clearly defining the specific requirement. Is the operation truly independent and does it need to commit or roll back regardless of the main transaction? 2. Assessing the risk. What are the potential consequences of the autonomous transaction failing or succeeding independently? 3. Evaluating alternatives. Can the requirement be met using standard transaction management or other PL/SQL constructs without the complexity and risk of autonomous transactions? 4. Implementing with caution. If an autonomous transaction is deemed necessary, it should be used sparingly, encapsulated within well-defined procedures or functions, and thoroughly tested to ensure it does not negatively impact the main transaction or overall data integrity. 5. Adhering to security and auditability standards. Ensuring that the use of autonomous transactions does not compromise security or create gaps in audit trails. Question 16. Governance review demonstrates that a critical batch process responsible for updating millions of customer records based on external feed data is experiencing significant performance degradation. The current implementation iterates through a cursor, fetching one record at a time and executing an individual update statement for each. Developers are tasked with re-architecting this process to improve efficiency and reduce execution time without compromising data integrity. Which of the following approaches best addresses this implementation challenge within the Oracle 11g PL/SQL environment? Option A. Implement a pipeline table function that performs the update operations as it returns data. Option B. Fetch all records into a PL/SQL collection and then use a for-all statement to perform the updates. Option C. Construct and execute dynamic SQL statements for each individual record update within the cursor loop. Option D. Continue using a cursor to fetch records one by one, but optimize the individual update statements where clause. The correct answer is B. Fetch all records into a PL/SQL collection and then use a for-all statement to perform the updates. Explanation. Scenario analysis. This scenario presents a common challenge in advanced PL/SQL development where performance optimization intersects with data integrity and maintainability. The challenge lies in identifying the most robust and efficient method to handle a large volume of data updates within a transactional context, ensuring that the solution adheres to best practices for Oracle 11g and avoids potential pitfalls like excessive locking or resource contention. The governance review highlights a need for a standardized, high-quality approach to such operations. Correct approach analysis. Implementing a bulk collect into a collection followed by a for-all statement is the best professional practice in this scenario. This approach significantly reduces context switching between the PL/SQL engine and the SQL engine, leading to superior performance for large data sets. The for-all statement executes the DML operation once for each element in the collection, but the Oracle SQL engine processes it in a single, optimized operation. This minimizes overhead and improves throughput, directly addressing the performance concerns raised by the governance review. It also maintains transactional integrity by performing the updates within a single PL/SQL block. Incorrect approaches analysis. Processing row by row using a cursor loop and executing individual update statements is inefficient. This method incurs significant context switching overhead for each row processed, leading to poor performance, especially with large datasets. From a professional standpoint, this demonstrates a lack of understanding of Oracle's bulk processing capabilities and can lead to system slowdowns and increased resource utilization, which is a failure in efficient resource management. Using a pipeline table function to perform the updates would introduce unnecessary complexity and is not the intended use case for pipeline functions. Pipeline functions are designed for returning result sets from PL/SQL to SQL, not for performing bulk DML operations. This approach would likely be less performant than a for-all statement and would violate principles of using the right tool for the job, indicating a lack of sound architectural judgment. Employing a dynamic SQL approach for each row update within a loop while technically possible, exacerbates the context switching problem and introduces security risks, SQL injection, if not handled with extreme care. This method is generally discouraged for bulk operations due to its performance implications and increased complexity in managing the SQL statements. It represents a failure in adhering to secure coding practices and efficient execution strategies. Professional reasoning. When faced with bulk data manipulation in PL/SQL, the professional decision-making process should prioritize performance, data integrity, and maintainability. The first step is to identify the volume of data involved. For large volumes, cursor-based row-by-row processing is almost always suboptimal. The next consideration is Oracle's built-in mechanisms for efficient data handling. The for-all statement, in conjunction with collections, is specifically designed for this purpose. Developers should consult Oracle documentation and performance tuning guides to understand these constructs. When evaluating different approaches, consider the number of context switches, the complexity of the code, potential for errors, and adherence to established best practices for the specific Oracle version being used. Question 17. Compliance review shows that a critical batch process responsible for updating customer account balances based on a daily transaction log is experiencing significant performance issues and occasional transaction failures. The current implementation uses an explicit cursor to fetch each transaction record and then executes an update statement for each record within the loop. Developers are tasked with optimizing this process to improve performance and ensure transactional integrity, while adhering to advanced PL/SQL best practices that discourage row-by-row processing for DML. Which of the following approaches would best address these requirements? Option A. Rewrite the process to use an explicit cursor, but optimize the individual update statements by adding hints to improve their execution plan. Option B. Fetch each transaction record using an explicit cursor and execute the update statement within the loop, but add a commit statement after every 100 records to reduce transaction log overhead. Option C. Refactor the process to use a single SQL merge statement that directly processes the transaction log against the customer account table, eliminating PL/SQL entirely. Option D. Fetch all transaction records into a PL/SQL collection, and then use a for-all statement to perform the update operations, incorporating SQL% bulk exceptions for error handling. Correct answer is D. Fetch all transaction records into a PL/SQL collection, and then use a for-all statement to perform the update operations, incorporating SQL% bulk exceptions for error handling. Explanation. Scenario analysis. The scenario presents a common challenge in advanced PL/SQL development, managing complex data structures and ensuring data integrity within a transactional context. The professional challenge lies in selecting the most robust and efficient method for handling a collection of records that need to be processed and potentially updated or inserted, while adhering to strict transactional boundaries. The need to avoid explicit cursors for performance and maintainability, as mandated by best practices for advanced PL/SQL, adds another layer of complexity. Furthermore, the implicit requirement to handle potential errors gracefully within the transaction is critical for data consistency. Correct approach analysis. The correct approach involves utilizing a collection, nested table, or vary populated from the source data, and then processing this collection using a for-all statement. This method is considered best professional practice because it significantly reduces context switching between the PL/SQL engine and the SQL engine, leading to improved performance compared to row-by-row processing with explicit cursors. The for-all statement is designed for bulk operations, making it highly efficient for DML statements applied to multiple elements of a collection. It also allows for error handling through the SQL% bulk exceptions clause, enabling the collection of errors without halting the entire transaction, thus promoting data integrity and providing detailed feedback for troubleshooting. This aligns with the principles of writing efficient and maintainable PL/SQL code, as emphasized in advanced PL/SQL training. Incorrect approaches analysis. One incorrect approach involves using an explicit cursor with a loop to fetch and process each record individually. This is professionally unacceptable because it leads to significant performance degradation due to excessive context switching. Each fetch and subsequent DML operation incurs overhead, making it inefficient for large datasets. Ethically, It represents a failure to apply learned best practices for performance optimization, potentially impacting system responsiveness and resource utilization. Another incorrect approach might involve fetching all data into a PL/SQL table without using for all, and then iterating through this table with a PL/SQL loop to perform DML. While this avoids explicit cursors, it still suffers from the performance penalty of row-by-row DML within the PL/SQL loop, similar to the explicit cursor issue, albeit with slightly less context switching. It fails to leverage the optimized bulk processing capabilities of for all. A third incorrect approach could be to perform DML directly within the cursor loop, without any error handling mechanism. This is professionally risky, as a single error in processing a record would cause the entire transaction to fail, leading to data loss or inconsistency for all processed records. This violates the principle of robust error management and data integrity, which are paramount in professional PL/SQL development. Professional reasoning. Professionals should approach such implementation challenges by first identifying the core requirement, processing multiple records within a transaction. They should then consider the performance implications of different PL/SQL constructs. The decision-making process should prioritize bulk processing techniques like for all when dealing with collections of data for DML operations, evaluating the need for error handling and choosing appropriate mechanisms, like SQL %bulk exceptions, is also crucial for ensuring data integrity and providing actionable feedback. Understanding the trade-offs between explicit cursors, PL/SQL loops, and bulk operations is key to writing efficient, maintainable, and reliable PL/SQL code. Question 18. Regulatory review indicates a need to store and process complex, hierarchical data structures within a single PL/SQL procedure for a financial reporting application. This data involves multiple levels of nested collections, where each item in an outer collection can contain its own collection of related items. Application requires that all operations on this data be atomic, and that the integrity of the nested relationships be strictly maintained throughout the transaction. The development team is considering different strategies for implementing this within Oracle 11g. Which of the following approaches best addresses the requirement for atomic transaction and strict integrity of nested data structures, while adhering to Oracle's object relational capabilities? Option A. Use PL/SQL collections, like nested tables or associative arrays, declared within the procedure's scope to hold the data, and manually manage their persistence and integrity by writing custom insert/update statements for each element. Option B. Define object types with nested table or vary attributes to represent the hierarchical data structure, and then process these objects within PL/SQL, ensuring that all operations are part of a single transaction. Option C. Flatten the nested collection into multiple independent relational tables, establishing foreign key relationships to simulate the hierarchy and manage updates across these tables within the transaction. Option D. Serialize the entire nested collection structure into a CLOB or blob data type, and process it as a single large string or binary object within the PL/SQL procedure. The correct answer is B. Define object types with nested table or vary attributes to represent the hierarchical data structure, and then process these objects within PL/SQL, ensuring that all operations are part of a single transaction. Explanation. The scenario presents a common implementation challenge in advanced PL/SQL development, managing complex data structures and ensuring data integrity within a transactional context. The professional challenge lies in selecting the most robust and efficient method for handling nested collections, particularly when these collections are part of a larger transaction that requires atomicity. Mismanagement can lead to data corruption, performance degradation, and violation of transactional integrity, which are critical concerns in any regulated financial or data-intensive environment. The correct approach leverages Oracle's built-in capabilities for handling nested collections within PL/SQL, specifically by using nested tables or vary as attributes of object types. This method aligns with best professional practices because it encapsulates the related data logically, maintains referential integrity where applicable, and allows for efficient manipulation and storage within the database. It adheres to the principle of data normalization and object-oriented design, leading to more maintainable and scalable code. From a regulatory perspective, this structured approach enhances auditability and simplifies data validation, crucial for compliance in environments where data accuracy and consistency are paramount. An incorrect approach involves manually managing arrays or collections outside of Oracle's object relational features, perhaps by serializing them into a club or blob. This is professionally unacceptable because it bypasses the database's inherent data management capabilities, making it difficult to query, update, or enforce constraints on the nested data, introduces significant risks of data inconsistency, and makes transactions involving this data prone to failure or partial updates, which is a direct violation of transactional integrity principles. Ethically, it represents a failure to utilize available tools effectively, leading to a less secure and less reliable system. Another incorrect approach might be to flatten the nested collection into multiple separate tables without a clear object relational mapping. While this might seem like a way to avoid complex data types, it often leads to a loss of the logical relationship between the parent and child data, making queries more complex and increasing the likelihood of join errors. This can compromise data integrity and make it harder to ensure that all related pieces of data are updated or deleted consistently, posing a risk to data accuracy and audit trails. The professional decision-making process for such situations should involve a thorough understanding of Oracle's advanced features, including object types and collection types. Developers should prioritize solutions that leverage the database's native capabilities for data management and integrity. A structured approach, considering factors like data relationships, transactional consistency, query performance, and maintainability, is essential. When faced with complex data structures, evaluating the benefits of object relational modeling against simpler, but potentially less robust, alternatives is a key step. Adherence to established design patterns and best practices for data modeling within the Oracle ecosystem is paramount for ensuring both technical excellence and regulatory compliance. Question 19. The assessment process reveals a requirement to process a nested collection of records within a PL/SQL stored procedure and return the results in a format that can be directly queried by SQL statements. The nested collection represents hierarchical data, where each parent record can have multiple child records. The procedure needs to flatten this hierarchy into a single, queryable result set. Which implementation strategy best addresses this requirement for efficient processing and SQL integration? Option A. Directly return the nested collection type from the stored procedure without any further processing or transformation. Option B. Implement a pipeline table function that iterates through the nested collection, flattens the hierarchy, and returns rows incrementally. Option C. Iterate through the nested collection within the stored procedure, extracting data from each level and inserting it into a temporary table. Option D. Serialize the entire nested collection into a club or blob and return this single value from the stored procedure. Correct answer is B. Implement a pipeline table function that iterates through the nested collection, flattens the hierarchy, and returns rows incrementally. Explanation. The assessment process reveals a common challenge in advanced PL/SQL development, managing complex data structures and ensuring data integrity within stored procedures, particularly when dealing with nested collections. The professional challenge lies in selecting the most efficient and robust method for processing these structures, while adhering to best practices for maintainability and performance, which are implicitly governed by the Oracle 11G development guidelines, and performance tuning best practices relevant to the 1Z0-146 exam. The correct approach, utilizing a pipeline table function, represents best professional practice because it offers a declarative and efficient way to process nested collections. Pipeline functions allow a stored procedure to return rows incrementally as they are generated, rather than building a complete collection in memory before returning it. This significantly improves performance and reduces memory consumption, especially for large datasets. This aligns with Oracle's recommendations for optimizing PL/SQL code that interacts with collections, promoting scalability and resource efficiency. An incorrect approach that involves iterating through the nested collection within the stored procedure and populating a temporary table row by row, while functional, is less efficient. This method requires explicit cursor management or bulk operations to insert data, which can be more verbose and potentially slower than a pipeline function for large volumes. It also introduces more procedural logic, increasing the potential for errors and making the code harder to maintain. From a performance perspective, it doesn't leverage Oracle's optimized collection processing capabilities as effectively. Another incorrect approach, attempting to directly return a nested collection type from a stored procedure without any specific processing or transformation, is often impractical for direct SQL consumption. While PL/SQL can handle nested collections internally, integrating them seamlessly into SQL queries typically requires a mechanism like a pipeline function or a user-defined object type that can be queried. This approach fails to provide a readily usable result set for SQL, hindering its integration with other database components and reporting tools. Finally, an approach that involves serializing the nested collection into a glob or blob and returning that, while a possible workaround for passing complex data, is highly inefficient for querying and processing the individual elements. This method treats the structured data as unstructured text or binary, requiring deserialization and parsing on the client or in subsequent PL/SQL code, which is computationally expensive and defeats the purpose of having structured data in the first place. It is a poor choice for scenarios where the individual elements of the nested collection need to be accessed or filtered within SQL. Question 20. The efficiency study reveals that a critical PL/SQL procedure, responsible for processing high-volume financial transactions, is experiencing significant performance degradation. This procedure utilizes bulk operations, specifically for-all statements, to insert and update records in multiple tables. The primary suspect for the bottleneck is the for-all statement itself, which is executing a series of insert and update statements. Which of the following diagnostic and optimization strategies would represent the most professional and effective approach to resolving this performance issue within the Oracle 11g environment? Option A. Analyze the execution plan of the SQL statements executed within the for-all loop and investigate potential issues with context switching and array fetch sizes. Option B. Increase the PGA program global area size significantly without first diagnosing the specific memory usage patterns of the procedure. Option C. Add multiple new indexes to all tables involved in the for-all operation, assuming that increased indexing will universally improve DML performance. Option D. Immediately rewrite the for-all loop to process records individually using explicit cursors to simplify debugging and isolate potential errors. The correct answer is A. Analyze the execution plan of the SQL statements executed within the for-all loop and investigate potential issues with context switching and array fetch sizes. Explanation. The efficiency study reveals that a critical PL/SQL procedure, responsible for processing high-volume financial transactions, is experiencing significant performance degradation. This procedure utilizes bulk operations, specifically for-all statements, to insert and update records in multiple tables. The challenge lies in identifying the root cause of the performance bottleneck without compromising data integrity or introducing new vulnerabilities, especially given the sensitive nature of financial data. The regulatory framework for this exam, Oracle 11g, Advanced PL/SQL, implies adherence to best practices in database development and performance tuning within the Oracle ecosystem. The correct approach involves a systematic and targeted investigation of the for-all statements execution plan and its interaction with the underlying data structures. This includes analyzing the impact of context switching, the efficiency of the SQL statements within the for-all loop, and the presence of any row-level locking or contention issues. Best professional practice dictates a methodical approach that prioritizes understanding the existing code's behavior before making changes. This aligns with the principle of least privilege and the need for auditable, reproducible results in financial systems. An incorrect approach would be to prematurely optimize by adding unnecessary indexing or altering the for-all statement structure without a clear understanding of the performance issue. For instance, blindly adding indexes without analyzing the query plan can lead to increased overhead for DML operations, negating any potential gains and potentially causing new performance problems. Another incorrect approach would be to revert to row-by-row processing within the loop, which, while simpler to debug in isolation, fundamentally undermines the performance benefits of bulk processing and is a step backward in efficient PL/SQL development. This would be a failure to leverage the advanced features of PL/SQL as intended, leading to suboptimal resource utilization. Professionals should approach such scenarios by first establishing a baseline of current performance. Then they should utilize Oracle's built-in diagnostic tools e.g. SQL trace, TK-Prof, explain plan to pinpoint the exact statements or operations causing the slowdown. Hypothesis generation and testing, focusing on one potential cause at a time, is crucial. This iterative process of diagnosis, hypothesis, and validation ensures that changes are data-driven and that the most effective solutions are implemented.